Great to be here. So today I'm going to talk a little bit about how you enable energy-efficient computing for AI and robotics. I know some of the themes in the panels for today's workshop also includes sustainability, so that's kind of what what we'll be discussing today. So we all know that there's been rapid growth in energy consumption for computing. Particularly, you've heard a lot of these staggering statistics from the data center about the data centers. Like in 2022, data centers account for 3% of global electricity, and then now it's expected to grow all the way to 8% by 2030, and it just continues to rise. And as a result of this, many of you might have heard that even these data centers and cloud service providers are investing in power plants to power these data centers. We know that one of the reasons why there's this rapid growth is due to AI, in particular deep neural networks, right? So we can see that there's this trajectory on the, you guys see my pointer? Yeah. On the left-hand side here that, it's almost like every year the amount, like the size of the network increases by an order of magnitude, which is very rapid, and this, of course, translates into a lot more computation. Okay. The other thing I just want to highlight, this is in the data center and like the use of AI in the data centers. It's also important to consider the fact that we have a lot of emerging applications that also use AI. So, for instance, if a data center approximately in 2021, Meta or Facebook was saying that you have 1 trillion inferences per day across their data centers. If you think of an emerging application like autonomous vehicles, where you have multiple cameras on the vehicle in order for it to understand its surroundings, and then you often have to run multiple neural networks to process the visual data that's coming in. You can imagine that just for one autonomous vehicle, it would take 22 million inferences per hour driven. And then if you scale that up, and that's not too much, like if you think about 1 million AVs, so that's less than 0.1% of the vehicles worldwide, that's around 22 trillion inferences per hour driven. Okay? So that's not to say that we shouldn't look into self-driving cars or AVs, but it's just, if you consider the scaling effect, it's not just the data centers that are consuming a lot of energy, but you're also consuming a lot of energy in a lot of these emerging, exciting applications that we're using AI. More closer also to my research, we also care about enabling energy-efficient AI on edge devices. So for example, something the size of the palm of your hands, maybe a smaller robot or your phone. There we also have challenges in terms of power and energy, because often if you think of a processor on these small embedded devices, they don't have a fan to cool it. So as a result, the computer chips that are doing the computing is limited to be under a watt of power. And a lot of often the compute that's necessary for a lot of these applications might be higher than that. Often on these smaller devices, you're also limited by the amount of energy that you have, by the size, weight, and cost of the battery. And so this is an additional challenge that we have on these smaller embedded devices. So what I'm interested or going to share with you today is some of the strategies that we take to enable energy efficiency for computing. Primarily it was targeted for these edge devices, but they also apply a lot to the cloud as well. Because now we care about energy efficiency across the board. Okay? And so hopefully my goal for all of you is at the end of this talk, you have an idea about where, how to basically connect energy with computing. So when you guys, launch and analyze all your data, how you're spending your energy. Okay, so I want to connect compute to carbon emissions in particular. So there's a couple of questions we want to think through when we want to think about how to make this connection. So first is, what do we actually want to compute? So what are the tasks that we're actually doing? What are the compute demands? And I'll get more into that. And this might impact, what type of algorithms you might want to use. For example, what kind of DNN architectures and models you want to use. So that we usually, from a, computer architecture standpoint, classify that as a workload. And so once you have these algorithms, they become a workload, you need to run that on some piece of hardware, some computer somewhere. So then when you talk about what is the computing hardware, which is going to be used to process this workload. So these two things together is what I would classify as how we actually compute. So there's what we compute, and then there's how we compute. That's often the main focus of my own research. So based on whatever given application, someone decides what they want to compute, and then we decide how we can compute it. So of course you have compute energy that drives this hardware to perform this computation. But this compute energy needs to come from somewhere. So it's often impacted by, what is the energy delivery to get the energy to the system. And as I mentioned, one of the challenges for computing hardware is it generates a lot of heat. So you need to cool it. So that actually also consumes a lot of energy. And then you have to think about what the energy source is, in terms of is it electricity, coal, whatever, renewables. And so it also is impacted by where you actually do the compute, and that's going to affect the relationship between carbon emissions and the compute energy. Basically, what is the carbon intensity of it? Of course, there's also, when you talk about carbon, you can also break it down to two types of carbon. There's the operational carbon, so like literally how we're translating the carbon emissions to compute energy to operate the hardware, but there's also the manufacturing costs of the carbon emissions. Actually, how do you manufacture the hardware? So that's what we would call embodied carbon. So what I'm going to try to cover in today's talk is what are the factors that impact each of these steps? What are the challenges that still exist? And then what are the possible solutions? Okay, so hopefully by the end of this talk you have a grasp of all these. Okay, so let's start with the computing hardware. That's the closest to my own area of expertise and research area. So the biggest challenge that we're facing right now is that transistors are not getting more efficient. So over the past couple of decades, many of you might have heard of things like Moore's law or Dennard scaling, which allow transistors to become smaller, faster, and more energy efficient. You can imagine that that's becoming more and more challenging to do as these transistors are getting smaller and smaller. And in general, if you look at the past decade or so, this has really kind of flattened out. Right, so Dennard scaling is over. Dennard scaling applies to the energy efficiency of the transistor. That's done. And then in terms of getting faster and more dense, that's very much slowing down as well with Moore's law, primarily due to cost. It's becoming more and more difficult to manufacture these small transistors. So as a result, you can't rely on general purpose computers like CPUs to get faster and more efficient. So it used to be that the computers don't change too much. It's just the components that we build it out of, which is the transistors, were getting better. So now you have to really start thinking about how can we redesign the computers from the ground up. And one of the common strategies for making things more efficient is to go from general purpose to more specialized or more domain-specific hardware. So you might have heard these terms before, like how do you really specialize for a given task, okay? The other thing is that there's been a lot of research looking at new devices and new materials to kind of supplement the fact that these transistors are not becoming more efficient. So now rather than always using the same type of transistors, you might use a combination of different types of transistors and components to make up for the fact that the transistors are not becoming more efficient. Okay, so this is what's going on in this space. Of course, all of these design choices sound great, but we also have to consider that it does impact manufacturing cost. And that would affect embodied carbon. So just as a very high level, if you have a very specialized hardware and you want to run new algorithms that the hardware doesn't support, then you'll have to buy new hardware, and that's going to reduce the life cycle of the hardware itself, okay? And that's going to affect its embodied carbon, because then you need to manufacture a new one. Okay, so if we're going to talk about hardware, our question should be like, if we're going to design specialized hardware for AI, where does the energy go, right? Because the whole idea is that we want to design new hardware that's energy efficient. And as it turns out, the energy is consumed by or dominated by data movement. So it's not actually, like many of you are familiar with deep neural nets, primarily the operation is multiplies and accumulates. And what you can see here is the energy cost for multiplications and additions at different precisions, right? Whether you have 32-bit floating point multiply or 8-bit integer multiply and so on, shown here in blue. But actually, what's more energy costly is reading the data from memory to deliver to that multiplier and then storing the result, right? So if we have a 32-bit multiply floating point, let's say it's 3.7 picojoules, reading just one input to that multiply from a very small memory, so 8 kilobyte memory, is already going to be 5 picojoules of energy. And for every multiplier, reading 2 inputs and then writing 1 out. And then even worse is if this memory, because this is a very small SRAM memory that's on the computer chip, often you want to store obviously more than a couple of kilobytes or even megabytes. You want to store at least gigabytes. Then you would typically have to go to an off-chip separate memory like DRAM. And then reading from off-chip DRAM is actually orders of magnitude even higher in terms of energy. Okay? So the takeaway from this is, number one, that data movement, like accessing the data and storing the data, is really high in terms of energy consumption, and the larger and further away the memory is, the more energy it would consume. So obviously, if we want to target, designing specialized hardware to reduce the energy cost, we should really target data movement. That should be the ultimate goal. Okay. So let's talk a little bit about what are some of the strategies that we can use for reducing data movement. Okay, so the high-level benefit of DNNs in general is that we know that all those max, multiplies, and cumulates are highly parallelizable, so high throughput is possible. The main challenge is the memory access is the bottleneck, right? So for every multiply and accumulate, you have 3 reads, so the filter weight, the feature map activation or the input, and then the partial sum for your accumulation, and then the result is a memory write of the updated partial sum. Okay, so it's a 4-to-1 ratio in terms of memory access to compute. And then, of course, in the worst case scenario, if you access this from DRAM, you'd be like each of these memory accesses would be 200 times more than the energy of one max. So this is terrible. But you do have some opportunities within the workload that you're processing to reduce the data movement. In particular, you have what we call input data reuse. So basically the same inputs, or say pieces of data that come in, you can reuse them multiple times for different operations. So ideas like you read it once from that very expensive memory and then use it multiple times. Okay, and then in the context of convolutional neural nets, you have convolutional reuse because the same filter is going to be scanned across the inputs, and you can imagine the activations and the weights are going to be reused multiple times. You often apply multiple filters to the same input feature map to generate multiple output channels. What does that mean? That means that each input is going to be reused multiple times across the different filters. Finally, for your filter reuse, so if you're going to process more than one image at a given time, like a batch size greater than 1, then the filter weight can be reused multiple times across the batch. And actually, some of you who've been training neural networks, that's why when you increase the batch size, that you're loading in, you speed up the processing because you're amortizing or exploiting this reuse. Okay, so given this reuse, we know this reuse exists in the workload. If you're doing LLMs, it also exists in terms of as long as you're repeatedly using the same weights for some input, or you're doing the input itself is going to be reused across multiple filters or weights, you're going to have this reuse. So then the challenge goes as follows. I know there's this reuse, and then I'm going to look at the hardware that I'm going to design. And typically, the hardware, or specialized hardware that people design for AI processing looks as follows. And they're all some small variant of this, which is they're going to be an array of processing elements, we just call them PEs. And basically, these processing elements just each contain multiplies and adders inside. They might also contain some small local memory nearby, typically maybe under a kilobyte, and then some control. And then you can communicate between the processing elements. They might also have a shared larger memory that we call a global buffer, maybe in the hundreds of kilobytes. And then the worst case, they go off to DRAM. And so the takeaway here is that if we look at the energy cost for each of these things, so let's say it takes 1x to do this multiply and accumulate, reading from this really small memory is also the same energy locally. Reading from your neighboring processing elements is going to cost a little bit more energy. And then you have reading from the buffer is going to be 6x, let's say, and then DRAM is 200x. And this is consistent with farther and larger memories consume more power. So the main challenge is, knowing what you have, the reuse pattern that you have, is that when you read something from DRAM, you want to move it all the way to this register file and then use it as many times as possible for as many computations as possible, okay, before kicking it out. And of course, the challenge here also is that this register's file is very small. So you have these huge neural networks. So how do you chop it up into these small chunks and then reuse it as much as possible here? An analogy of trying to understand how this would work would be I know some of you have traveled here and so on. So the question goes as follows. If you wanted to complete a certain amount of work, what would you, and the easiest thing you can store it in is your bag that you've brought here. It's very limited in terms of capacity. And pretend we're not dealing with computers right now. Pretend you have to do paper, okay? So there's a limited capacity. What would you store in that bag today so you can get the most amount of work done in that limited capacity? And then if you look at the different PEs, it'd be if you're traveling with some of your colleagues or friends, maybe you could also kind of schedule with them what should they also bring. So you can share papers between the rest of you to also, as a team, do more work. But obviously, sharing data between your team members is going to be more effort than reaching into your own bag. So that's the P. A global buffer would be like, okay, if you need to store, okay, this is where you're traveling. If you're traveling into like your hotel room, you could store much more there. But obviously, it's much more energy to go all the way back to your hotel room to grab the papers to do more work. And then finally, DRAM would be like your original home. It's like very expensive to go back here, but you could store all the data that you actually needed for what you're doing. Okay, so that's basically the way to think through this problem, right? It's very cheap to locally access the data, but you're very limited. And so how do you schedule and collaborate amongst your friends and minimize the energy cost of moving this data around? That's the mindset. And you can imagine this is a very large design space. And then there's also a choice in terms of how big to make each of these levels of memory. So some of our work that targeted this was some of this Iris work that was Joel Emmer. And so again, it's like specialized hardware that really focuses on reducing memory access. At the time, it allowed you to do like image classification under 1/3 of a watt. And because of the specialization in the data movement, efficient data movement, you can have like an order of magnitude reduction compared to GPU. So this is some research work, but I also want to emphasize that in practice, these days, there's a lot of specialized hardware that's going on based on this exact same principle of trying to reduce data movement and specialization. So we already saw these traditionally maybe more software companies or data center operators invest in building specialized chips for DNN. So for example, Google had the TPU back in 2016, and now they're already on TPU 4 or 5. Amazon designed some specialized hardware for inference and then training in 2020 itself, right? So I think like hopefully, and then like generally speaking, again, the types of problems that they're thinking about is how to reduce data movement, how to specialize, while still trying to have some flexibility, because when you design these chips, they often take at least a year to do, but we know these models continue to evolve and they want to make sure, so the challenge there is also trying to think through how do we keep it flexible enough so that we can support, the models that will come in the future. Okay, so that's one particular aspect. Another important thing to think about is to reduce data movement. I mean, the key thing is you're trying to store as much data as possible on these low-cost memories. And this becomes a challenge when you're dealing with sparse data, right? So we know, like, for example, tensor sparsity for sparse data processing can vary widely depending on what type of applications you're looking at. If you look at the tensor sparsity within a tensor itself, so here we have zeros are in white, non-zeros are in black. You can see that the sparsity pattern will change depending on the tensor, and not just depending on the tensor itself, but also within the tensor itself, it also varies, like depending on which region of the tensor you're actually looking at. Okay? So this is going to be a challenge because of the following things. So remember I was saying that we're going to take this workload, or whatever inputs you have, and then break it into chunks. And the whole idea is you're trying to store as much as possible these chunks in that local memory. But if your data is sparse, it's hard to kind of predict how big of a chunk you actually want, because some of those values are going to be 0. You don't really have to store it, right? So the idea would be the more data that you can store, bigger chunk that you can store in your bag, your very small bag, then the more efficient your system will be. But because the variation in sparsity, like it's very hard to predict when I grab a chunk how many of those things are actually going to be non-zero, how much space it's actually going to take. It makes it a very challenging problem. There's some strategies that people take to try and address this. One is like, okay, I'm going to spend the time and actually look inside this chunk and then count the number of non-zeros that I have so I know exactly how much space it has. And then each chunk that I select is always going to directly fit into the size of the memory that I have. Okay, so I'm really utilizing whatever memory that I have. It's going to be very efficient. But if you think about, does tensor operations and so on, first of all, the chunks that you're picking are going to be very irregular in shape. So it's actually very hard to implement. And then also it's hard to figure out, if these are two inputs, what's the corresponding chunk in the other input that you're going to use to do that computation. Okay, so the other strategy is like, all right, forget about that. I'm going to pick, always make sure that my chunk is the same size. It's much easier to implement, right? But of course, the problem is if my chunk is always kind of the same size, how much space it takes is going to vary, right? So sometimes it's going to really utilize the memory that I have, and then sometimes it's going to be very inefficient and used. So it's like if you grabbed a bunch of, okay, let me go back to the analogy. You grabbed a bunch of paper to bring in your bag, but like, only like 1/10 of it is useful for your actual processing. The rest of them is like noise. So then it was a waste of space, right? You get a lot less work done. Okay, so this problem actually has a nice analogy to flying and overbooking, right? So airlines have the same problem, which is as follows. They would like to fill their plane, all the seats in their plane, and then so they sell a certain amount of tickets, but obviously sometimes people cancel, people miss their flight, and so on. And so if they only sold the number of tickets that lined up with the number of slots in the plane, you're going to get a bunch of empty seats. It's going to be very inefficient, right? So you're not going to fully utilize the capacity of your plane. So instead, what they do is they do overbooking, right? They're going to sell more tickets than they actually have seats for, and then the hope is that, although people drop out, you're still going to really, fill up the capacity of your plane, and it's going to be much more efficient. Make sense? Okay. And so you can imagine the same thing with the tensor. You're going to, if you pick a tile that's exactly the size of the buffer, you might have a whole bunch of empty space. It's very inefficient. But if you pick a tile size that's much bigger than your buffer, then the idea is that, you're going to have a better capacity full. Of course, we all know that what is the downside of this? It's that if you pick it too big and then you're actually at high capacity, then you're going to have to bump a passenger, right? And then similarly in the hardware, you need to have a case where you also handle the bumped data. You can't just be like, oops, I can't fit it in. So with this analogy, you can also, as long as you have a mechanism that basically says, if you have too much data, I have a way to handle it without my hardware just stopping to work. But then you can guarantee the fullness, or not guarantee, you can increase the fullness of your capacitors. And so basically you have two strategies to do that. So one is called the Taylor's approach, which allows us to handle the bumped data, right? So that if it's bumped, the hardware can still function. And then in terms of how much you actually want to book, like how big should this tile size be, we have a fast way to do that, because you also want to compute that quickly, called Swift tiles. And we're also very proud of the naming of this paper. But anyway, so if you're into that, I encourage you to read the paper just for the eggs. Okay, there's a lot of eggs in there. Okay, so what is the impact of this? So I think we compare it to a couple of different approaches. One is that assuming you don't know how many non-zeros, you don't check at all, so you always just assume it's dense. You don't take any benefit of that. The other is you actually look at where the non-zeros are, and then you design for the very worst case scenario. You always guarantee that it'll fit. And then you have the case where you don't exactly know. You have like 90% of the time it fits, 10% of the time it gets bumped out. And then so what is the impact of this? Let me just skip ahead. So if you compare to the case where you don't check anything at all, you're going to get order of magnitude speed up, like 50x speed up and 22 times faster. But even if you design for worst case scenario, as long as you have hardware that's flexible enough to adapt to the case where you overbooked, so you're not designing for the worst case scenario, you're just allowing things to overflow, you get a 2x speed up better than designing for worst case. Okay, so the high level message here is that there's a lot of variability in your workload, and that's another challenge for hardware. How do you actually adapt to changes in your hardware? And you want to do it in a graceful manner so that you're not, if you always design for worst case, you might be wasting a lot of resources. That's the kind of high level takeaway. Okay, so that's reducing data movement. The next approach that people are taking is, well, can I just reduce the cost of the data movement? Like, I'm still going to move things around, but can I reduce how much it costs? So one big area that people are looking into is kind of the concept of computing in memory. What does that mean? So normally when we do this, multiply and accumulate, we have to read input from some memory and the weight data from some memory, and then we store the output somewhere. And so the whole idea or the concept here is that can we actually embed the compute in the weight memory itself, so at least it saves the data movement for the weights. This is a huge area of research. I won't get too much of the details, but maybe some of you might remember this from high school physics. But the idea here is that if each storage element is represented by a resistor, and the conductance of the resistor is the weight, then if you use Ohm's law, you apply a voltage across, the voltage is proportional to the input. And then if you use Ohm's law, Basically, the current is going to be the product of the two, and then if you use Kirchhoff's current law where you connect the wires together, you get this free addition. But anyways, even if that doesn't make sense, there's a way to kind of leverage the memory storage element to do the computation itself, so then you reduce the data movement. The main challenge of all of this is that it becomes analog computing. I don't know if you guys are familiar with the analog computing, but basically you're very sensitive to variations in these resistors. So if they're slightly different, you're going to notice it. This is compared to like digital, you don't have that issue. And then also your compute is in analog domain, but you're still storing in digital domain. So you need these like analog to digital conversions and so on. But nonetheless, there's been a huge amount of research in this space trying to kind of also develop these new devices that can be programmed for different bits of weights and then try to minimize their variation and use them for this computation. And so, in fact, if you look at commercially, IBM is doing a lot of research in this space. So when you see this analog computing, by the way, that's typically this stuff that we're just talking about here. There have been startups that also have been looking at trying to do this as well, I think, as an example. Okay, so that's one way. Another way is like, all right, let's just not use electricity. Why don't we use light? Because light doesn't take that much energy to travel. In fact, it's like, in terms of moving the photon, it can be independent of distance, right? And then in some ways, the multiplication can be performed passively. You can imagine your input is how bright the light is, and then you have some kind of light splitter, right? How much light you actually how much you attenuate it by is your weight, and then all the light comes together and accumulates. That's the accumulation. That's the gist of it. So there's been a lot of research in this space as well. And again, there's been startups looking at using computing with light to try and use the fact that, light is cheap to move around. And so this addresses the cost of the data movement itself. And then some of our own work in this space is that because there's so many people looking at all these different types of devices to do this type of computing, so how do we kind of bridge these different research communities and model the impact of these different devices, whether it be light or these new resistors, and combine it with a lot of the architecture work itself. Okay, so that's computing hardware. Now I'm going to just lightly talk about computing algorithms and also kind of the sources of the energy. So let's talk about the algorithms itself, which is maybe a little more aligned with folks here. Okay, so there's a lot of effort in designing efficient deep neural network algorithms. Generally speaking, I would say that they can be classified into 3 different categories. You have a lot of people working on sparsity, right? So basically that means, setting some of these weights to 0 and then trying to exploit that fact by, anything times 0 is 0. So you skip those operations. And if there's a lot of zeros, you can compress things and then, again, reduce data movement, which we saw was really important. You can imagine also coming up with more efficient network architectures, meaning reducing like the certain dimensions and the ranks of the tensors that you use. And then a lot of work on reducing precision. So rather than using 32-bit float, can you do 8-bit fixed? Can you all the way down to binary? And so on. Of course, the challenge in all of these is that it does impact the quality of result, right? It's not like you can willy-nilly make these things, apply these. You have to consider the impact on overall quality of result. The other thing to also consider is that often there's a focus of reducing the number of max and weights. But in reality, what we really care about is the impact on energy and latency, right? That's the reason why you're doing it. And as it turns out, it's actually quite a bit of a challenge because the number of max and weights are not good proxies for energy and latency. So for instance, this is a plot from Google's mobile vision team. It's showing the number of MAC operations on the x-axis and then the latency on the y-axis. And what they show is, for instance, for a given number of multiply and accumulates, you can have a 2x swing in terms of your latency. Or for a given latency, you can have a 3x swing in terms of your max. So just because you reduce the number of max doesn't necessarily mean that your hardware is going to run faster. Okay, it really depends on how it interacts with the hardware. Similarly, there's been a lot of focus on reducing the number of weights in the neural network. But if we look at the breakdown of where the energy is going, it's not just the weights, the data movement of the weights, but you also care about the data movement of your input feature maps and your output feature maps. So you need to consider all types. So just because you have a small number of fewer parameters or weights in your neural network doesn't necessarily mean it's going to be more energy efficient either, because the feature maps can also be very large and they move a lot. Okay? And so there's been this big area, not big, but like an effort to kind of really incorporate these hardware metrics into the design of the neural network algorithms. So it's kind of like, in the objective function or the optimization, you're actually going to target, reducing the energy and latency as opposed to just reducing the number of max and weights, right? So for example, there's work looking at energy-aware pruning, which basically means rather than removing weights that are small, just small in magnitude, you actually think about, oh, how much energy is this weight going to consume, and I'm going to remove the weights based on the energy cost. And then similarly, you can imagine rather than to get enough feedback from the hardware itself, you're going to insert the hardware into the feedback loop and automatically kind of adapt the neural network for a given platform. So this is some work that we did in collaboration with Google's mobile vision team because they want to make sure that you can adapt the neural net for any given platform that they run their mobile apps on. Because you want to automate that process, but basically the high-level message, you want the hardware in the loop so you can get hardware metrics like energy and latency actually measured as opposed to just trying to count the number of operations. Okay, and if you are excited about this whole space of how to compute, we have written textbooks on this, and we teach a class about this at MIT. Okay, so that's how to compute. Let's move on to where to do the computing itself. And so where you actually want to compute is a lot of it often depends on the energy source. So it's that will dictate your, how carbon emissions relate to energy. That's basically based on the carbon intensity. So how much carbon per kilowatt hours you generate. And of course, it varies by region. If you're talking about renewables, obviously this is going to vary for the time of day. Daytime, you're going to get a lot more renewables in terms of solar or when it's windy. So that's great. So the idea here is that you want to kind of shift your data to these particular regions and process it where you have the lowest carbon intensity. There's also the energy delivery. So when you go from energy to compute energy, that's the second step. So I deliver energy into my data center, but how much energy actually arrives at the computing server, it's going to be affected by the power conversion, right? Because they use different wattage or different voltages, and then the cooling costs. So often they classify this as the power usage effectiveness, although there's some controversy about this, which is the energy divided by the compute energy. And then there's a decision also about whether or not you want to do the computing on device or in the data center itself. So there's some arguments that say, okay, if you want to, depending on your application, you might want to do the processing on device if you're constrained by things like latency, privacy, communication, or you want to do it in the cloud, in the data center. On device is also often very distributed, so you're not, grounded at some certain location. But anyways, the high-level takeaway from this is I think there's a lot of, so in terms of energy delivery, I think a lot of these larger data centers have really worked hard to push this PUE down to 1. Okay, I think it's very close, so I think that's why. The kind of a researchy or things that people continue to explore are dealing with the energy sources. So can you move the data and do the processing in a location where the carbon intensity is low? I think the big change of that challenge of that is the impact of communication costs, right? It's not cheap to just send all of your data to this other region to do it. So I think that's one issue. Latency is also another issue, right? So if you want real-time feedback for your stuff, you might not be able to wait for it to be transmitted somewhere else and come back, or wait for a certain time of day for it to be processed. So this is still an open challenge, and there's a lot of active research in that space. Okay, so finally, I'm going to talk about what we actually want to compute. So what to compute? There are some opportunities there. Maybe you can reduce the amount of data that's needed. So for example, you might be able to exploit data reuse since data movement is expensive. So for instance, previously I worked on video compression. There's a lot of redundancy in video, right? So maybe you don't have to process every single frame. Maybe you can leverage some of the correlation across the frames and reduce how much processing you're actually doing. There might be data efficient techniques and models that kind of exploit prior knowledge. So maybe if you have a prior, you don't need to use as much data to do the processing. I think you guys are more the experts on this, or things like transfer learning. I think it's also important to evaluate the result trade-off. So what is the cost-benefit evaluation? So is the little boost of 0.1% accuracy worth this huge amount of carbon emissions? I mean, you've all heard those statistics about how a Google search using AI is 10x more energy than a regular search. Is the quality of result really 10x? I think I'll leave you to judge that. So yeah, you just definitely have to think about the quality of result for a given task. And then you want to maybe reduce the amount of requests you're doing. So Reproducibility, at least from a research point of view, would be nice, so then you don't have unnecessary requests. Also good for advancing research. In the context of my own research, and this is now more a little bit more the robotic stuff, you would imagine you encounter a similar type of thing in a robot. You have limited energy. One of the key tasks in robotics is to understand how far objects are so you don't crash into them, to understand your environment. Previously you would use these sensors that you actively, you send a pulse out and wait for it to come back, and that tells you how far something is. That's very expensive. So of course, people start applying neural networks to this, and they're saying if I have a regular passive camera, just an RGB image, can I apply a neural network to it and then just predict the depth locations of the different pixels? So that will save the sensor power. This is an active area of research. Okay. Of course, the challenge with all neural networks is if there's a mismatch between your training data and your deployment data, right? So you trained up your neural network in a certain region, and now you've deployed your robot into a new area, and it might not be predicting depth correctly. And so what you might want to do is retrain your neural network for this depth estimation in this new region. And so you can imagine what you could do is just keep on always training it. Once you're in a new area, you just always train it. But that's going to be very expensive. So instead of that, what you want to do is spend, or what we propose doing, is spend some energy trying to decide when you should stop training and when you should start training again, right? So you kind of need a way to kind of estimate what is if I were to train again, would I be able to improve, and by how much? And only then you kind of start training again. This is the analogy my student likes to make in terms of it's kind of like studying, right? How much more should I study this chapter more if you have an exam, or should I move on? Is it worthwhile, kind of thing? So you want to say how much energy should I spend on each of these types of things? In this particular work that or we did, looking at this type of deciding when to train, and accounting for these two measurements of how much possibly more could I learn, and is it possible to even can I learn it, and is there more to actually learn? What they showed is basically by doing this decision making, you can get the same accuracy as training all the time with only 30 to 60% of the training. So I don't know exactly how it is, but you have to think about it for your own work, in terms of how often you need to run a job or retrain or run. It's good to think, can you add some decision-making mechanism to decide when to train and update and when not to. But of course, for all of this, the one final challenge you might have is that even if you make everything efficient, the problem is Joven's paradox, right? So some of you might be familiar with this. The more efficient you make something, then the more people will use it. And so this is, generally speaking, an overall challenge for society. So yeah, this is just something to take into account. Anyways, so what are the key takeaways for this talk? There's obviously increasing demand for AI, and it increases carbon footprint to compute. There's many efforts from the hardware to the algorithms for use case to try and improve the energy efficiency and the carbon efficiency of compute. But there's also a huge number of challenges. So then that means for all of us, many exciting research opportunities. Okay. I want to acknowledge my students and sponsors and collaborators who work on this. And then if you really want to dive into more about this topic, I can invite you to check out some of our resources online. Okay, with that, I am done. Thank you very much.